A rhythmic pulse beats from deep space, a cosmic drum echoing across the void. This is the sound of a pulsar, a rapidly spinning neutron star. These objects are the collapsed cores of giant stars, compressed into spheres so dense a single teaspoon would weigh billions of tons. By the end of this journey, you will uncover 25 of their greatest secrets, from the bizarre matter in their hearts to signals that defy the laws of physics. How can a star's corpse become the universe's most precise clock? And what happens when two of these monsters collide? What cosmic mystery do you think could rewrite the rules of reality itself? That impossible density is our first great mystery, a puzzle locked within the heart of the star's corpse. We call it a neutron star, but the truth is, we have no certain idea what it truly is inside. Picture taking the entire mass of a mountain and crushing it down into a single sugar cube. That is the reality of neutron star matter. A single teaspoonful brought to Earth would weigh billions of tons, sinking through the planet's crust as if it were air. But what gives it this incredible property? The leading theory suggests that under such immense gravitational pressure, electrons are forced into atomic nuclei, merging with protons to create a solid ball of neutrons. This neutronium would be the hardest, densest substance in the universe. Yet many physicists suspect this is just the beginning. The core, crushed to pressures we cannot replicate on Earth, might undergo a more radical transformation. The neutrons themselves might shatter, breaking down into their constituent parts, a soup of free-floating quarks. This quark-gluon plasma would be a state of matter not seen since the first fleeting moments after the Big Bang. And there is an even more speculative and terrifying possibility. This quark soup might stabilize into something called strange matter, a perfect, stable form of matter that is more fundamental than anything we know. Some theories even suggest that a single speck of this strange matter could infect normal matter, converting an entire star into a strange star upon contact. This is not just an academic debate. Unlocking the secret of what lies within a neutron star is a direct probe into the fundamental forces of nature, a test of quantum chromodynamics under the most extreme conditions imaginable. The true nature of this ultra-dense matter remains one of the greatest unsolved problems in all of physics. Just when we think we understand these cosmic clocks, they stutter. A pulsar's spin is renowned for its metronomic stability, a rhythm so precise it rivals our best atomic clocks. Yet without warning, that steady beat can falter and then jump, its rotation suddenly and inexplicably speeding up for a fraction of a second. Astronomers call these events glitches, and they are one of the most baffling behaviors in the neutron star catalog. Imagine a spinning ice skater who, without any visible effort, suddenly spins faster. This is the essence of the pulsar glitch, a phenomenon that defies our basic intuition about spinning objects. How can a city-sized object weighing more than our sun spontaneously accelerate its own rotation? The leading explanation takes us back into the star's bizarre interior, to a place where physics becomes truly alien. Deep within the neutron star's crust, theorists believe a superfluid exists. This is no ordinary liquid. It is a quantum sea of neutrons that flows without any friction or viscosity whatsoever. This superfluid is threaded by countless tiny whirlpools called vortices, which are normally pinned in place by the star's rigid crystalline crust. The crust and the superfluid are locked in a delicate dance, but they are not perfectly coupled. As the pulsar loses energy and its crust slows down over millennia, the superfluid inside, unaffected by this breaking, can end up spinning faster than the crust that contains it. The glitch may occur when the strain becomes too great, and these superfluid vortices suddenly unpin themselves and rush outward. This transfer of momentum from the faster spinning interior to the slower spinning crust gives the entire star a sudden, observable kick. Another possibility involves starquakes. As the neutron star spins down, its shape must subtly change, becoming more spherical. The incredibly dense crust under unimaginable stress might fracture like a giant crystal, causing a sudden shift in the star's moment of inertia and making it spin faster, just as that ice skater spins faster when they pull their arms in. These glitches are not merely cosmic curiosities. They are our only direct seismic probes into the heart of these enigmatic objects. Each glitch sends a shiver through the star that astronomers can measure, revealing clues about the nature of its internal layers, the hardness of its crust, and the strange physics of its quantum core. By studying these sudden stutters, we are effectively taking the pulse of a monster, listening to the echoes from a realm where matter itself is pushed to the breaking point. These cosmic stutters are not the only interruptions in the signals from deep space. From the darkness between galaxies come bursts of energy so powerful they outshine entire stars, yet they last for less than the blink of an eye. These are fast radio bursts, and for years their origin was one of astronomy's most profound puzzles. A single burst can release more energy than our sun emits in 80 years, all compressed into a few thousandths of a second. The first ones discovered seemed to be one-off events, cosmic catastrophes that destroyed their source. Theories for their cause ranged from evaporating black holes to the collapse of exotic stars, or even, more speculatively, signals from advanced alien civilizations. The mystery only deepened when astronomers found a repeater. A source, now known as FRB 121102, began firing off bursts again and again, proving that whatever was creating them could survive the immense release of energy. This was the crucial clue that pointed directly to neutron stars. The leading suspect is a specific, terrifying type of neutron star known as a magnetar. Imagine a stellar corpse with a magnetic field so intense it could erase the data on every credit card on Earth from halfway across the solar system. The crust of a magnetar is under unimaginable strain from this magnetic field. Astronomers propose that these fields can become so twisted that they suddenly snap and reconnect, a process known as a starquake. This event unleashes a colossal shockwave through the magnetar's atmosphere, accelerating particles to near light speed and producing a brilliant, fleeting flash of radio waves that we detect as a fast radio burst. Other theories suggest that the bursts could be powered by highly magnetized plasma crashing onto a neutron star, or perhaps from material ejected from a pulsar wind nebula interacting with its surroundings. While magnetars remain the prime candidate, the sheer diversity of fast radio burst behaviors suggests we may be dealing with more than one cosmic culprit. Each new flash from the void is a potential Rosetta Stone, a millisecond message that could finally reveal the violent, magnetic heart of a distant stellar corpse. Even these brilliant radio flashes are dwarfed by the true titans of cosmic violence. Gamma-ray bursts are the most powerful explosions known to exist, second only to the Big Bang itself. For a few fleeting seconds, a single gamma-ray burst can outshine every star in 100 billion galaxies combined. And we now have compelling evidence that the birth cries of some of these cosmic monsters are directly tied to the death spirals of neutron stars. The shortest and most intense of these bursts, lasting less than 2 seconds, are classified as short gamma-ray bursts. For decades, their origin was a profound mystery. Then, in August 2017, astronomy entered a new era. Observatories around the world detected a cataclysm 130 million light-years away. The key signal was not light, but a ripple in the fabric of spacetime itself, a gravitational wave. This ripple was the unmistakable signature of two neutron stars locked in a final, fatal dance. For over 100 million years, these stellar corpses had been circling each other, their orbits decaying as they bled energy in the form of gravitational waves. In their last moments, they circled thousands of times per second, closer and closer, before finally smashing together. The collision itself is almost beyond comprehension. It does not simply create a bigger neutron star. The combined mass is too great, and the object immediately collapses into a newborn black hole. But in that chaotic instant, as the two ultra-dense cores merge, a fraction of their material is flung out at nearly the speed of light. This material forms a swirling, superheated disk around the newborn black hole, and from the poles of this system, a narrow jet of radiation and particles erupts into the void. If one of those jets is pointed directly at Earth, we see it as a short, unimaginably bright flash of gamma rays. The event in 2017 confirmed this entire model in a single observation. The gravitational wave signal told us two neutron stars had merged. Seconds later, gamma-ray telescopes saw the burst. In the days that followed, observatories saw the glowing aftermath, a kilonova, which revealed the forge where the universe's heaviest elements like gold and platinum are created. This single event tied together the fates of neutron stars, black holes, gravitational waves, and the very elements that make up our world. It revealed that the collision of these dead stars is a fundamental engine of creation and destruction, seeding the cosmos with the building blocks of planets and life, while simultaneously unleashing the most focused fury since the dawn of time. This magnetic fury finds its ultimate expression in the magnetoflare. While a pulsar glitch is a subtle stutter in timing, a magnetoflare is a full-throated cosmic scream. These events are the largest explosions in our galaxy since the Big Bang, yet they originate from an object barely 20 kilometers across. A single one of these giant flares can release more energy in a tenth of a second than our Sun will emit over 100,000 years. To grasp that scale, picture capturing the total solar output for a period longer than human civilization and compressing it into a single, blinding flash. The source of this almost inconceivable power is the magnetar's unimaginable magnetic field, a force a quadrillion times stronger than the field that protects our Earth. A magnetic field this powerful fundamentally warps the reality around it. It becomes so strong that it can actually twist the vacuum of empty space itself, a phenomenon known as vacuum birefringence. The magnetic stress on the neutron star's solid crust is equally immense. This crust, a lattice of iron nuclei 10 billion times stronger than steel, is not indestructible. It is under constant, unbearable strain. The leading theory for what triggers a giant flare is a starquake of cosmic proportions. The magnetar's crust, unable to withstand the twisting magnetic forces any longer, fractures. This is not a small crack. It is a global rupture, a seismic event that rearranges the star's entire surface. When this happens, the pent-up magnetic energy is released in a cataclysmic reconnection event. Think of it as the universe's most powerful short circuit. The magnetic field lines, which had been twisted into impossibly complex knots, suddenly snap and reconfigure themselves into a simpler, lower energy state. In that instantaneous reconnection, all the stored magnetic energy is violently converted into a firestorm of radiation, accelerating particles to nearly the speed of light and creating that brief, terrifying flash of gamma rays and X-rays. The mystery that remains is what exactly pushes the system over the edge. What is the final straw that causes the crust to finally break? Is it a slow, relentless buildup of internal magnetic pressure, or could it be triggered by an external influence like the impact of a large asteroid onto the magnetar's surface? Each detected flare is a rare and precious data point, a fleeting glimpse into the behavior of matter and energy under conditions so extreme they cannot be recreated anywhere else in the universe. The aftermath of a stellar cataclysm should leave a clear signature, a spinning beacon in the cloud of its own debris, but sometimes the universe hides its most anticipated prizes. For over 3 decades, astronomers have trained the world's most powerful telescopes on the expanding cloud of supernova 1987A, the closest stellar explosion witnessed in nearly 400 years. At its heart, they expected to find a newborn neutron star, a pulsar flashing its rhythmic signal into the cosmos. Instead, they have found only a profound and puzzling silence. Where is the stellar corpse? The leading theory is one of cosmic concealment. The supernova's expanding shockwave may have created a thick shroud of gas and dust, a dense cocoon that absorbs the pulsar's radiation before it can escape. It would be like trying to see a lighthouse beacon through the thickest, most impenetrable fog imaginable. The light is there, but it is smothered by the very aftermath of the explosion that gave it birth. Another possibility is that the neutron star is simply not what we expected. Perhaps its magnetic field or its spin axis is aligned in such a way that its narrow beam of radio waves simply never sweeps across our line of sight. We could be staring right at it, but because its lighthouse beam points elsewhere, it remains invisible to our instruments. Or it could be an exceptionally faint pulsar, its emissions too weak to penetrate the distance and the intervening cosmic static. Yet the most dramatic and unsettling possibility is that there is no pulsar to find. The core of the star that exploded may have been just over the mass limit for neutron star formation. Instead of stabilizing as a spinning orb of ultra-dense matter, it could have continued its catastrophic collapse, instantly becoming a black hole. This would defy our standard models of stellar death, suggesting that under certain conditions, a giant star can skip the neutron star phase entirely, its core vanishing from the universe the moment it is born. Each new observation of this supernova remnant is a search for a ghost. Did a pulsar ever form, or was it swallowed at birth? The answer holds the key to understanding the final moments of stellar collapse, a process that, even when it happens right in our cosmic backyard, can still guard its ultimate secret. This cosmic cannibalism reveals a predator in the stellar graveyard, the Black Widow pulsar. Named for the spider that consumes its mate, these neutron stars are engaged in a slow-motion feast. The story begins in a binary system where a pulsar and a smaller, sun-like star orbit one another. Over eons, the pulsar's intense gravity begins to siphon material away from its companion. This stolen gas and dust, carrying immense angular momentum, spirals onto the pulsar's surface, acting like a cosmic whip that spins it up to incredible speeds. The once slow pulsar becomes a millisecond pulsar, rotating hundreds of times every second. But this is where the relationship turns fatal. Having been spun up by its partner, the pulsar now unleashes a relentless torrent of high-energy radiation from its powerful magnetic fields and intense particle winds. This deadly beam sweeps across the companion star, slowly but surely boiling it away. The stellar material is blasted into space, creating a vast cloud of vaporized gas that trails behind the binary pair. With every orbit, the companion star grows smaller and more misshapen, its mass steadily evaporating into the void. Astronomers can actually detect these systems by the shimmering, heated cloud of the companion's remains. This brutal process teaches us about the ultimate fate of such binary systems. The question is, how far will it go? Will the pulsar completely devour its partner, leaving behind a solitary millisecond pulsar as the only testament to its cosmic crime? Or will the evaporation process halt, leaving a tiny, burnt-out stellar core as a permanent trophy? Each Black Widow system is a cosmic clock, ticking down the final moments of a star being destroyed by the very object it helped to create. They are extreme laboratories for studying how matter and energy interact in the most hostile environments, showing us that even in death, some stars are not content to rest in peace. Even the most reliable cosmic beacons can fall silent without warning. Pulsars are famous for their steady, metronomic rhythms, but some exhibit a deeply strange behavior known as nulling. For hours or even days, their radio pulses simply vanish, as if a switch has been flipped off in the depths of space. Then, just as mysteriously, the signal returns, picking up its rhythm as if nothing had happened. This is not a sign of the pulsar's death, but a temporary, perplexing quiet. The phenomenon becomes even more bizarre with mode changing. Here, a pulsar does not go quiet, but abruptly shifts its entire personality. Its pulse pattern, its brightness, and even the shape of its radio waves will suddenly change, switching to a completely different and stable configuration. It is as if a musician, after playing a complex symphony for years, instantly switched to a simple folk song without missing a beat. What could possibly cause such a fundamental and rapid transformation in an object with the mass of a sun? The answer is believed to lie not in the solid star itself, but in the ethereal, electrified cloud that surrounds it, the magnetosphere. A pulsar's brilliant beam is generated by a complex river of charged particles, a plasma, being accelerated along its powerful magnetic field lines. Theorists suggest that nulling may occur when this plasma flow is suddenly choked off. The engine that creates the radio waves simply stalls, perhaps because the supply of particles from the pulsar's surface is temporarily interrupted. Mode changing, however, points to a more dramatic rearrangement of the entire magnetic environment. The pulsar's magnetic field, under immense stress, might suddenly reconfigure itself like a tangled ball of rubber bands snapping into a new, simpler shape. This global shift would change the paths that the plasma flows along, effectively redirecting the lighthouse beam and creating an entirely new pulse pattern for us to observe. Some models even propose that the magnetosphere can exist in two distinct, stable states, and a small trigger, perhaps a tiny starquake, is enough to flip it from one mode to the other. These silent pauses and altered voices are more than just cosmic quirks. They are direct messages about the stability or the surprising instability of the most powerful magnetic fields in the universe. Each time a pulsar nulls or changes mode, it offers us a fleeting glimpse into the turbulent, invisible weather raging around a stellar corpse. That map is a message in a bottle cast into the cosmic ocean. Etched onto the golden records carried by the Voyager probes is a pulsar map, a celestial fingerprint designed to lead any finder back to our solar system. It charts the precise rotational periods of 14 specific pulsars with their positions relative to the Sun. The idea is sublime in its simplicity. These pulsars are cosmic lighthouses, each with a unique, identifiable blink. An advanced civilization could, in theory, compare the recorded rhythms against the pulsars in the sky, triangulating our home world's location and the epoch from which the probe was launched. It is a map built not on static stars, but on the steady beats of time itself. Yet this beautiful concept rests on a profound and unsettling assumption that these pulsars are perfectly stable clocks, reliable over millions of years. We now know this is not entirely true. Our own observations have revealed that pulsars can glitch, null, and change their modes. Their rotations gradually slow down as they lose energy. While scientists chose pulsars with exceptionally stable periods, the map cannot account for the unpredictable. What if one of the 14 key pulsars on the map experiences a giant glitch 1,000 years from now, permanently altering its rhythm? What if a magnetar flare from a nearby star completely disrupts the signal of another? The map could become corrupted, its directions leading to a cosmic dead end. This transforms the golden record from a simple address into a deeper philosophical question. Are we relying on cosmic permanence in a universe defined by change? The pulsar map is a testament to human ingenuity, but it is also a gamble on the long-term stability of the most violent objects in the galaxy. We can only hope that the steady beats we recorded will still be echoing unchanged for the eons it may take for someone to find our message and read it. The steady rhythm of a pulsar is a comforting constant in a chaotic universe, but one known as PSRB 1931+24 defies that expectation with a schedule of its own. This is not a random stutter or a temporary glitch. It operates on a precise and baffling cycle, turning its radio beacon on for roughly 1 week, only to fall completely silent for the next 30. It is a cosmic lighthouse with a pre-programmed timer, and its behavior challenges everything we thought we knew about how these engines work. For that 1 week of activity, it behaves like a perfectly normal, middle-aged pulsar, spinning steadily and beaming its signal across space. Then, as if obeying some unseen cosmic command, it shuts down. Its radio emissions vanish, and it remains in this dormant state for a month before roaring back to life and repeating the cycle. This is not a case of a dying star, but a system that has been reliably switching between these two states for years. The leading theory to explain this bizarre on-off behavior points directly to the pulsar's magnetosphere, that dynamic realm of plasma and magnetic field lines where the radio beam is born. Scientists propose that this pulsar can exist in two completely separate and stable configurations. Think of it as a cosmic light switch that can be in either the on position or the off position, with a complex mechanism that automatically flips it every few weeks. In the on state, the plasma flow is stable, particles are being accelerated, and the radio beam is generated. For reasons we do not fully understand, this state becomes unstable. The plasma flow is somehow choked off, and the entire system collapses into its second stable state, the off position where the radio beam simply cannot form. After a period of about a month, the conditions must slowly rebuild until the system can snap back into its active state and the cycle begins anew. What triggers the flip? Is it a buildup of electrical current that eventually shorts out the system? Could it be linked to a slow, cyclical starquake that periodically disrupts the magnetic field? This pulsar is a profound mystery because its behavior is so clean and predictable, yet the mechanism behind it remains utterly elusive. It forces us to ask if other pulsars have similar hidden cycles. Their steady beats merely a phase in a much longer and much stranger rhythm we have yet to detect. Beneath the thin atmosphere of a neutron star lies a crust of incredible strength and complexity. This is not a shell of rock or ice, but a crystalline lattice forged under pressures that crush matter into bizarre new forms. Picture a solid where the atomic nuclei themselves are packed together, touching one another, all swimming in a degenerate sea of free electrons. This crust is a material 10 billion times stronger than steel, a rigid shield capable of supporting monumental mountains on its surface. Yet the true mystery lies deeper, where the pressure becomes so immense that this orderly structure begins to break down into something even stranger. Physicists call this phase nuclear posture. As you descend through the crust, the gravitational squeeze forces the nuclei to merge into giant, elongated tubes like strands of cosmic spaghetti. Further down, the pressure increases again, and these tubes themselves merge into flat sheets, a layered structure they call nuclear lasagna. It is a realm where the very distinction between a single nucleus and a continuous medium blurs into nothingness. This nuclear posture is not just a curiosity. It may be the strongest material in the entire universe, and its properties directly shape the life of the neutron star. The elasticity and sheer strength of this deep crust are thought to be the source of the massive starquakes we detect as magnetar flares. When the crust finally fractures under magnetic stress, the energy released depends entirely on how much strain this nuclear posture could withstand before it shattered. These exotic shapes may also pin the superfluid vortices inside the star, playing a crucial role in the glitches that suddenly speed up a pulsar's spin. We cannot recreate this material in any laboratory on Earth. Its existence is inferred from complex models and the subtle behaviors of these distant stellar corpses. Every glitch and every starquake is a message from this hidden realm, a clue to understanding the architecture of a substance that defines the very limits of matter itself. Surrounding the silent, spinning heart of a pulsar, a ghostly nebula can bloom, a vast cloud of glowing energy that outshines the star itself. The most famous of these is the Crab Nebula, the sprawling, colorful aftermath of a supernova witnessed on Earth in the year 1054. At its very center lies a pulsar spinning 30 times every second, and it is this tiny, dense object that powers the entire nebula, lighting it up like a cosmic lantern. The question is, how does a stellar corpse only 20 kilometers across energize a cloud of gas that stretches for light years? The answer lies in an invisible hurricane blowing from the pulsar, a phenomenon known as the pulsar wind. This is not a gentle breeze of starlight, but a relentless supersonic gale of charged particles, electrons, and their antimatter counterparts. Positrons ripped from the pulsar's surface and accelerated to nearly the speed of light by its immense magnetic fields. This wind carries away a tremendous amount of the pulsar's rotational energy, acting as a primary brake that gradually slows its spin over millennia. But the wind itself is invisible. The brilliant nebula we see is born from a cosmic collision. The pulsar wind, moving at almost light speed, slams into the much slower moving debris of the ancient supernova explosion, the ejecta that was blown off the star long ago. This collision creates a violent standing shock wave, a boundary where the wind is abruptly forced to decelerate. It is at this shock front that the magic happens. The chaotic energy of the impact turbulently scrambles magnetic fields and forces the particles to crisscross the shock boundary repeatedly, each time gaining a little more speed, like a ball being bounced between two rapidly approaching walls. Through this process, known as diffusive shock acceleration, the electrons and positrons are boosted to truly fantastic energies, becoming what physicists call cosmic rays. When these ultra-relativistic particles are then whipped around by the nebula's magnetic field, they emit a brilliant synchrotron radiation across the entire electromagnetic spectrum, from radio waves to the most powerful gamma rays. This is the light we see. The Pulsar Wind Nebula is therefore a cosmic engine, a testament to the transformative power of a neutron star. It takes the raw, rotational energy of a collapsed sun and converts it, through wind and shock, into a persistent, glowing echo that can illuminate the depths of space for thousands of years. Gravity's patient pull is always waiting. Every neutron star exists in a precarious state of balance, where the immense inward crush of its own gravity is held at bay only by a mysterious quantum pressure from within. This leads to one of the most fundamental questions in all of astrophysics. What is the maximum mass a neutron star can possibly reach before this balance shatters and it collapses into a black hole? Finding this upper limit is not just about measuring a number, it is about probing the very nature of matter itself. The current champion, the heaviest neutron star we have confidently observed, is named Pulsar J0740+6620. This monstrous object, spinning hundreds of times per second, has a mass equivalent to 2.08 times our own Sun, all compressed into that same tiny 20-kilometer sphere. We know this precise weight because it exists in a binary system with a white dwarf star. By meticulously tracking their orbital dance, astronomers can apply the laws of physics to weigh them with extraordinary accuracy, much like you could determine the mass of the Sun by watching the planet's orbit around it. This measured value over two solar masses is a crucial piece of experimental data. It immediately rules out many theoretical models of the neutron star interior that were too soft, models which predicted that such a heavy object would have already collapsed. The fact that this pulsar exists tells us that the material inside a neutron star must be incredibly stiff, able to resist gravitational collapse with astonishing strength. Yet this observed limit is only part of the story. Theoretical calculations suggest the true maximum could be higher, perhaps as high as 2.5 solar masses. The exact figure depends entirely on the equation of state, a complex formula that describes how the pressure of neutron star matter changes with its density. Think of it as the ultimate material science test, determining how much weight a spring can support before it catastrophically buckles. A softer equation of state means the matter is more compressible, leading to a smaller, denser star with a lower maximum mass. A stiffer equation of state allows for a larger, less dense star that can support more weight against gravity. Every new neutron star mass measurement, especially those pushing the upper boundaries, acts as a key, locking out equations of state that are too soft or too stiff. The holy grail would be to find a neutron star sitting right on the precipice, so massive that any further addition of matter, even a single grain of cosmic dust, would cause it to vanish into a black hole. Discovering that precise tipping point would finally tell us which equation of state governs reality, revealing the true nature of the universe's strongest material. Until then, every heavy neutron star we find is a sentinel on the edge of oblivion, silently testing the laws of physics under the most extreme conditions imaginable. Drifting through the empty black between stars, solitary giants roam in absolute silence. These are the isolated neutron stars, rogue planets on a cosmic scale, but with the mass of a sun compressed into a city-sized sphere. Unlike the pulsars flashing from within supernova remnants or the black widows feasting on companions, these wanderers travel utterly alone. They are dark, fast-moving ghosts, and their very existence poses a difficult question. How does a star's corpse end up so completely divorced from its past? The most dramatic explanation is a cosmic kick. When a massive star goes supernova, the explosion is not always perfectly symmetrical. If more neutrinos or debris are blasted out in one direction than another, the newborn neutron star can be kicked away from its birthplace like a rocket. Recoil velocities can be staggering, propelling these stellar cinders through the galaxy at speeds exceeding 1,000,000 miles per hour. At such velocity, a neutron star can quickly escape the thin, glowing cloud of its own supernova remnant, leaving the evidence of its violent birth far behind. Within a few 100,000 years, it is a lone voyager in the galactic dark. Another path to isolation comes from a broken partnership. Many stars are born in binary systems. If one star explodes as a supernova, the sudden loss of mass can drastically weaken the gravitational bond holding the pair together. The explosion itself might give the neutron star a substantial kick, easily enough to fling it clear of its stunned companion. The result is two solitary objects hurtling away from each other on separate paths through the galaxy, their ancient union forever severed. Detecting these dark wanderers is a tremendous challenge. Without a pulsing radio beacon or a glowing nebula to mark their location, they are nearly invisible. The key is to look for the faint, black-body glow of their incredibly hot surfaces. A newborn neutron star's surface can be over 1,000,000 degrees, emitting most of its light in high-energy X-rays. Space telescopes designed to see in this energetic spectrum are our primary hunters of these rogues. They scan the sky looking for tiny, dim points of X-ray light that are not associated with any known supernova remnant or companion star. The hunt has had some success, revealing a small population of these enigmatic objects. One famous example is the Calvera star, an isolated neutron star relatively close to us, yet floating in a curiously empty region of space. Its discovery confirmed that such lone wolves are a real and distinct class of object. Each one we find is a fossil from a cataclysm long past, a silent witness to the chaotic forces that shape stellar death. Their solitary journeys remind us that the galaxy is not a static museum, but a dynamic arena where even the dead can be sent flying on epic, million-year voyages into the unknown. The silent paths of these cosmic wanderers may hold the key to hearing the universe's faintest hum. Across the galaxy, astronomers are tuning an instrument of impossible scale, a detector built not from steel and glass, but from the spinning corpses of dead stars. This is the Pulsar timing array, a network of the most stable millisecond pulsars, used as a web of precision clocks to sense the subtle stretching of spacetime itself. Each of these pulsars acts as a single blinking node in a galactic GPS system. By monitoring their rhythmic pulses with radio telescopes over years and even decades, scientists can detect minuscule deviations in their arrival times, variations so small they amount to less than 1/1,000,000th of a second. A single such glitch might be a starquake, but a correlated drift seen across dozens of pulsars spread throughout the galaxy can only mean one thing: the space between us and those pulsars is being warped by a passing gravitational wave. The primary signal they are hunting is not the sharp chirp of two stellar mass black holes colliding, but something far more grand and pervasive: the gravitational wave background. This is theorized to be a constant, low-frequency rumble, a cacophony of waves overlapping from countless merging supermassive black holes in the hearts of distant galaxies. Throughout cosmic history, as galaxies collided and merged, their central black holes, weighing billions of suns, are thought to have eventually spiraled together. Each of these monstrous mergers would have sent powerful ripples through the fabric of space-time, and the combined signal from all such events across the universe would create a stochastic background, a gravitational hiss that fills the cosmos. Detecting this background would be a monumental achievement. It would provide direct, observational proof that supermassive black holes do indeed merge, confirming a key prediction of our model of galaxy evolution. But it would do far more than that. By studying the statistical properties of this hum, scientists could census the population of these giant binaries throughout time, revealing the history of galaxy assembly from the earliest epochs. It might even reveal unexpected sources such as signals from cosmic strings, hypothetical defects in the fabric of spacetime from the first moments after the Big Bang, or the gravitational waves generated by the rapid inflation of the universe itself. The data from these pulsar timing arrays is already showing a promising common noise signal that has the characteristics of this long-sought background. While not yet confirmed as a definitive detection, the rhythmic ticks of these cosmic clocks are beginning to trace the outline of a symphony played by the most massive objects in the universe, a deep, resonant chord that has been echoing since the dawn of time. These silent clocks can transform into brilliant X-ray beacons when they find themselves in a cosmic partnership. In the deep reaches of space, a neutron star locked in a gravitational embrace with a normal star can become something else entirely, an X-ray binary. Here, the neutron star's immense gravity acts as a celestial vacuum, relentlessly pulling gas from its companion. This stolen material does not fall directly onto the surface. Instead, it forms a swirling, flattened disk of superheated plasma, an accretion disk spiraling inward at nearly the speed of light. Friction within this disk heats the gas to temperatures of millions of degrees, causing it to glow with an intense, high-energy fury, primarily in X-rays. The sheer power of this process is staggering, outshining our own sun by a factor of 100,000. But the true mystery unfolds at the very edge of the neutron star itself. As this torrent of hydrogen and helium rains down onto the star's impossibly dense surface, it accumulates in a layer that grows hotter and more pressurized with each passing moment. This sets the stage for a spectacular and violent phenomenon, a thermonuclear explosion right on the surface of a stellar corpse. Astronomers know these events as Type I X-ray bursts. In a matter of seconds, the entire accumulated layer of fuel ignites in a runaway fusion reaction, a stellar flash fire that rips across the neutron star's surface. For 10 to 100 seconds, the system can become one of the brightest X-ray sources in the entire sky, a beacon of raw nuclear power. Then, just as quickly, it fades as the fuel is exhausted and the process of accumulation begins anew. These bursts are not just cosmic fireworks, they are precise natural laboratories. By studying their light curves, the way they brighten and fade, physicists can probe conditions that are impossible to recreate on Earth. They can measure the gravitational red shift, a subtle stretching of light caused by the neutron star's powerful gravity, which gives us an independent check on its mass and size. They can study the nuclear physics of rapid proton capture, a process that forges rare, heavy elements in these blasts. Each burst is a fleeting experiment in extreme physics, a chance to watch the laws of nature pushed to their absolute limit on a cosmic scale. The first one was found almost by accident, a mystery hidden in the data. In 1967, a young graduate student named Jocelyn Bell Burnell was reviewing charts from a new radio telescope when she noticed a peculiar, persistent signal. It was a series of sharp, rhythmic pulses arriving every 1.337 seconds with a precision that was utterly unnatural. The signal was so perfectly periodic that the only conceivable explanation, half-seriously proposed, was an artificial beacon from an extraterrestrial civilization. The source was whimsically nicknamed LGM-1 for Little Green Men. The true answer, when it was finally confirmed, was perhaps even more astonishing than Little Green Men. This was not a message from aliens, but the discovery of the first pulsar, a rapidly spinning neutron star. The lighthouse model explained it beautifully. The beam from its powerful magnetic poles swept past Earth with each rotation, creating the clock-like pulse. Yet, solving one mystery only revealed another. How does nature construct such a flawless timepiece from the chaotic debris of a supernova? The formation is an act of cosmic alchemy. When a massive star collapses, its core contracts violently, and like a spinning ice skater pulling in their arms, this conservation of angular momentum causes the newborn neutron star to rotate at incredible speeds. Its magnetic field, also compressed, becomes intensely focused into two powerful beams. The perfect clockwork we observe is a direct result of this incredible spin and the stability of its magnetic axis. But this precision is not eternal. The very act of beaming energy into space through radio waves and its pulsar wind slowly saps its rotational energy. Over millennia, the pulsar's spin will gradually decay and its rhythm will slow. PSRB 1919+21, that first discovered pulsar, is a testament to this aging process. Its once rapid pulse has now widened to a period of several seconds, a slow, steady tick compared to the frantic beats of younger pulsars. The enduring mystery is not just how they are born, but how they maintain such stunning regularity across human timescales, their rhythmic beats echoing long after the stellar explosion that created them has faded into history. That silent journey through the void is often far from a gentle drift. Many neutron stars are cosmic cannonballs, hurtling through the galaxy at speeds that can exceed 800 kilometers per second, fast enough to travel from Earth to the Moon in under 10 minutes. These extraordinary velocities are known as neutron star kicks, and their origin is a fundamental puzzle in stellar death. How can a supernova explosion, the demise of a star, function as the most powerful rocket engine in the universe? The leading theory points to an inherent imbalance in the cataclysm itself. If the supernova explosion is not perfectly spherical, if just 1% more neutrinos and debris are ejected in one direction than another, the newborn neutron star will recoil in the opposite direction, just like a balloon shooting across a room when you let the air out. This recoil can provide the tremendous kick we observe, but what creates this crucial asymmetry in the first place? The prime suspect is a violent, turbulent convection that occurs deep within the collapsing star in the moments before the explosion. As the core implodes, immense heat generates rising and sinking plumes of ultra-hot matter, a chaotic churn that could easily break the explosion's symmetry and give the nascent neutron star a powerful shove. A more exotic and compelling theory gives a central role to the neutron star's unbelievably powerful magnetic fields. In this model, the magnetic field is not a passive passenger but the engine of the kick itself. Imagine the newborn neutron star as a powerful electromagnet. Intense heat generates a flood of neutrinos, and as these ghostly particles stream outward, they can interact with the ultra-strong magnetic field. If the field is not symmetrical, it can act like a one-way mirror or a lens, preferentially scattering more neutrinos out one particular side of the star. The recoil from this directional neutrino rocket could then accelerate the neutron star to incredible speeds. This mechanism could explain the most extreme kick velocities ever recorded, which seem to defy explanations based on hydrodynamic turbulence alone. The challenge for astronomers is untangling which process dominates. Does the kick come primarily from lopsided matter ejection, or is it the subtle push of a magnetic neutrino rocket? Or is it a complex combination of both? Each new high-velocity neutron star we discover is a clue, its speed and trajectory a frozen record of the final, violent moments of its birth. By studying these stellar speedsters, we are learning to read the hidden asymmetries in stellar death, revealing that the universe's most powerful explosions are never perfectly round. Deep within the crushing heart of a neutron star, a more profound transformation may be waiting. The quark-nova hypothesis dares to suggest that some neutron stars are not the final state of matter, but merely a penultimate step. Imagine the pressure rising past a critical threshold, so immense that the neutrons themselves can no longer hold their structure. They disintegrate, shattering into a soup of their fundamental components, up quarks, down quarks, and strange quarks. This would create a star within a star, a core of pure, free-floating quarks. If this quark core becomes unstable, it could trigger a second, even more violent explosion, a quark nova that completely obliterates the neutron star from the inside out. The observational evidence for such an event would be spectacular and distinct. Unlike a supernova, which is powered by the collapse of an iron core, a quark nova would be an explosion of pure, fundamental energy released from the phase transition of matter itself. Theorists suggest it could produce a superluminous supernova, an event far brighter than any normal stellar explosion, and one that would fade in a very specific, rapid way. The debris would be rich in heavy elements, but with a unique isotopic signature as the quark matter reassembles into normal atomic nuclei. The hunt is on to see if any of the bizarre superluminous supernova we have already recorded could fit this profile. Did we witness a star die twice, first in a supernova to create a neutron star, and then moments or even days later in a quark nova that finished the job? This is more than just an exotic idea. It is a potential window into the very moment that matter itself changes its fundamental nature, revealing a hidden layer of reality beneath the familiar world of protons and neutrons. The profound silence of an isolated neutron star might hide a secret interaction with the universe's most elusive substance. There is a deeply speculative yet fascinating theory that these ultra-dense objects could be cosmic traps for dark matter. Throughout the galaxy, countless weakly interacting massive particles, or WIMP, are thought to flow unseen through everything. They barely notice normal matter, passing through the entire Earth as if it were a ghost. But a neutron star is different. Its gravity is so intense and its matter is so densely packed that a dark matter particle passing through it has a much higher chance of being slowed down and captured. Over billions of years, these captured particles could slowly accumulate, sinking into the very core of the star. They would annihilate with each other or simply gather, adding their invisible mass to the neutron star's already incredible density. The consequence of this slow, steady accumulation could be catastrophic. If enough dark matter builds up in the core, it could potentially tip the star over its maximum mass limit. The delicate balance between outward pressure and inward gravity would shatter in an instant. The neutron star would no longer be able to support its own weight, and it would undergo a sudden, silent collapse into a black hole, vanishing from the visible universe without a supernova or any flash of light. This theory offers a potential solution to a long-standing puzzle. We observe many stellar mass black holes out in space, but our models of stellar evolution sometimes struggle to explain how all of them formed from supernova alone. Could some of these black holes be the end result of dark matter poisoning, a slow internal collapse triggered by an invisible guest that moved in over the eons? While this remains a highly theoretical idea, it forges a startling link between the largest mystery in cosmology, dark matter, and the most extreme objects in the stellar graveyard. It suggests that the ultimate fate of a dead star might not be written in the light it emits, but in the shadowy, cumulative embrace of the dark universe itself. The most unexpected of solar systems circles a cosmic tomb. In 1992, astronomers made a stunning discovery. The first confirmed planets ever found outside our own solar system were not orbiting a star like our Sun, but a pulsar named PSRB 1257+12. This pulsar, a stellar corpse spinning over 160 times per second, was found to be the gravitational anchor for at least 3 small, rocky worlds. The existence of these pulsar planets was nothing short of revolutionary, proving that planets could form in the most hostile environments imaginable. The central mystery is how these worlds came to be. A pulsar is born from a supernova, a cataclysm that should have vaporized any pre-existing planets and blasted their remains into the void. The leading theory paints a dramatic picture of destruction and rebirth. This pulsar likely once had a companion star, a sun-like partner. As the pulsar fed on its companion in a Black Widow-style relationship, it may have entirely consumed the star, shredding it with its gravity and radiation. The debris from this stellar destruction would have formed a vast, swirling disk of dust and gas around the pulsar, a second-generation protoplanetary disk. From the ashes of one dead star, new worlds could then coalesce, born from the wreckage of the old. These are not worlds as we know them. Bathed in the pulsar's relentless torrent of X-rays and high-energy particles, their surfaces would be sterilized, any atmosphere stripped away by the stellar wind. The question of life seems almost absurd, yet the laws of physics allow for a sliver of possibility. If one of these planets were a water world with a sufficiently thick global ice crust, that ice could act as a shield protecting a subsurface ocean from the radiation above. Tidal heating from the pulsar's powerful gravity could keep this hidden ocean liquid, much like the subsurface seas suspected on moons like Europa or Enceladus. In such a dark, abyssal environment, entirely independent of sunlight, could some form of extreme life exist? It is a staggering thought that the most stable, life-sustaining environment for light years around might not be under a warm sun, but deep within a frozen world, huddling for warmth in the deadly glare of a spinning stellar corpse. That single event in August 2017, known as GW 170817, gave us more than just confirmation, it gave us a symphony. For the first time, we did not just see the universe, we heard it. The gravitational wave observatories LIGO and Virgo detected the characteristic chirp of 2 neutron stars spiraling together, a rising frequency that ended in a silent crash. But this time, the dark event was illuminated. Across the globe and in space, telescopes swiveled to the same patch of sky, capturing a brilliant flash of gamma rays and then a slowly fading glow across every wavelength of light. This was the kilonova, the radioactive aftermath of the collision, and its light carried the signatures of newly forged elements. The analysis was stunning. It revealed that this single event created a vast cloud of gold, platinum, and other heavy elements, with a mass perhaps hundreds of times that of our entire planet. In one observation, we learned that the jewelry we wear and the rare metals in our electronics were born in the violent deaths of stellar corpses. Yet, for all it revealed, the event left behind a profound and quiet mystery, what was left at the heart of the cataclysm. The gravitational wave signal stopped at the moment of merger. Did the 2 neutron stars immediately form a black hole, or did they first create a single, monstrous object, a hypermassive neutron star that spun with impossible speed, briefly defying collapse before finally succumbing to its own weight? The difference is critical. A hypermassive neutron star surviving for even a few milliseconds would have radically altered the environment, blasting the surrounding debris with neutrinos and potentially creating a different mix of heavy elements. The long-term X-ray and radio observations of the aftermath have been ambiguous, with some data suggesting the presence of a stable, long-lived magnetar injecting energy into the cloud, while other interpretations point more cleanly to a swift collapse into a black hole. The remnant object, whatever it was, has never directly revealed itself. We are left with the echoes of a crash and the glittering dust it left behind, wondering if we witnessed the instant birth of a black hole or the brief, defiant last stand of the densest matter in the universe. The universe's most precise clocks can sometimes run backwards. While most pulsar glitches involve a sudden, mysterious speed-up, a handful of magnetars have done the exact opposite, slamming on the brakes in an event astronomers call an anti-glitch. One of the most famous examples occurred with a magnetar known as 1E2259.2+594, a stellar corpse already famous for its violent outbursts. For years, its spin was slowing down at a steady, predictable rate as expected. Then, without any warning, it suddenly slowed down even more. Its rotation had effectively taken a sudden, tiny step backwards, as if an immense, unseen hand had reached out and grabbed it. This is the opposite of everything we understand about these objects. A normal glitch is explained by the idea of a faster spinning superfluid inside transferring its momentum to the crust. But an anti-glitch defies that simple model. How can a star that is constantly losing rotational energy somehow lose even more in an instant? The theories to explain this backward step are as extreme as the phenomenon itself. One compelling idea points to a violent stellar wind. A magnetar's magnetic field is so powerful that it can literally rip particles from the star's solid crust and fling them out into space at nearly the speed of light. Theorists suggest that during an anti-glitch, the magnetar might experience a sudden, colossal ejection of this kind. If a massive blob of charged particles is thrown off the surface, it would carry a huge amount of the star's angular momentum with it. Just as a spinning ice skater slows down when they extend their arms, the magnetar would abruptly slow its spin as this material escapes its gravitational grip. Another, even more dramatic possibility involves the star's interior. Perhaps the superfluid core, for a brief moment, spins slower than the crust. If the vortices in this quantum fluid were to suddenly unpin and move, they could transfer this slower momentum to the crust, effectively applying a brake to the entire star. Or the star's own magnetic field, twisted into a complex, unstable knot, might violently snap into a new, simpler shape. This global reconfiguration could act like an internal anchor, sapping rotational energy and causing the sudden slowdown. Each anti-glitch is a rare and precious event, a paradox that challenges our core understanding of how these magnetic monsters work. They remind us that for all we have learned, the interior of a neutron star remains a place of profound mystery, capable of behaviors that still defy our predictions. There is a final, frantic speed limit written into the fabric of space and time itself. A neutron star can spin only so fast before the immense centrifugal forces at its equator overwhelm the unimaginable gravity holding it together, tearing the entire star apart in a catastrophic explosion. This theoretical breaking point is known as the mass shedding limit, and it is a violent dance between two of the universe's most fundamental forces. Calculations suggest this ultimate speed is around 716 rotations every single second. At that rate, the star's equator would be moving at a significant fraction of the speed of light. The current record holders, the millisecond pulsars, push terrifyingly close to this edge. Pulsars like Pulsar J1748-2446 spin over 700 times a second. Each rotation of this city-sized object, weighing more than our sun, happens in less than 1/500th of a second. The fact that we see so many of these ultra-fast spinners, yet none have been observed breaking through that 716 Hz barrier, is a powerful clue. It tells us that this limit is not just a theoretical curiosity, it is a real physical wall that nature enforces. The mystery is not just the limit itself, but what exactly determines its precise value. The exact spin where a neutron star flies apart depends critically on the stiffness of the ultra-dense matter in its core, the same property that sets its maximum mass. A star made of softer, more compressible matter will be smaller and denser, and it can spin faster before its equator reaches light speed. A star made of stiffer, more rigid matter will be larger, with its equator farther from the center, and it will hit the breakup speed at a slower rotation rate. So, every millisecond pulsar we discover is not just a cosmic speed demon, it is a direct probe of the star's internal architecture. The fact that we see none spinning faster than the predicted limit strongly suggests that the equation of state for neutron star matter is relatively stiff, preventing the existence of the very smallest, fastest spinning objects. This invisible barrier, defined by gravity and nuclear physics, stands as a permanent check on the ferocity of a dead star's spin, a fundamental rule that even the most extreme objects in the universe must ultimately obey. This relentless spin, however, is a temporary defiance of an inevitable end. Across timescales that dwarf the current age of the universe, every neutron star faces a final, quiet mystery. What is the ultimate fate of these cosmic cinders? The most straightforward path is a slow, dark fade. Over trillions of years, a neutron star will radiate away its immense residual heat, its brilliant light and X-rays dimming until it becomes a cold, solid sphere of ultra-dense matter, a black dwarf. This would be a frozen monument, a perfect crystal of nuclear material drifting in absolute zero darkness, its internal clockwork stilled forever. Yet the universe may not allow for such permanent monuments. The laws of quantum physics suggest that even the most stable structures are not truly eternal. One profound possibility is proton decay. If the proton, a fundamental building block of all matter, is not perfectly stable but has a finite lifespan, then the very substance of the neutron star is built on a timer. After an almost inconceivable period, perhaps 10 to the power of 34 years or more, the protons and neutrons within the star's core would spontaneously disintegrate. The entire structure would slowly evaporate into a faint mist of light particles and radiation, vanishing without a trace from the cosmos. Another speculative fate involves quantum tunneling. Given enough time, the particles in a neutron star could, through sheer random chance, tunnel through their gravitational confinement. It would be like a ball spontaneously rolling out of a deep bowl without being pushed. For a single atom, this is a negligible chance, but for the septillions of particles in a neutron star over near infinite time, it becomes a statistical certainty. The entire star could, in a sense, quantum evaporate, dissolving over an epoch so vast it makes the current age of the universe seem like a single heartbeat. These are not just thought experiments, they are tests of the most fundamental laws of nature. The final state of a neutron star tells us whether matter is truly permanent, or if everything we see is merely a temporary arrangement in a cosmos where even the most solid objects are, in the end, just fleeting patterns in the dark. From the bizarre quantum soup in their hearts to the gravitational ripples they send across the cosmos, these 25 mysteries reveal that neutron stars are far more than stellar corpses. They are nature's ultimate extreme laboratories, each one a natural experiment that pushes the laws of physics past their breaking point. They challenge our understanding of matter, energy, space, and time, from the strange matter that might lurk within their cores to the anti-glitches that make them spin backwards. They are the universe's most precise clocks and its most powerful magnets, the seeds of gold and the engines of gamma-ray bursts. They wander the galactic dark as silent ghosts and blaze as beacons in brilliant nebulae. Their collisions shake the fabric of space-time, and their slow fade into cold, dark dwarfs asks the most profound questions about the permanence of matter itself. So, as this journey ends, the real question begins. Which of these cosmic enigmas captured your imagination the most? Was it the destructive dance of the Black Widow pulsar, the silent puzzle of the missing supernova remnant, or the terrifying possibility of dark matter collapse? Share your thoughts and never stop looking up, for the universe is still whispering its greatest secrets, one pulsar beat at a time.